In this video, I will show you how a three-phase inverter works. So it works about the same in both directions. So if you're interested in a three-phase rectifier, you can also watch this video. So the link for the Simulink model is in the description. So if you want to try it, go ahead. So I will also show you how to implement a deadbeat controller for the inverter. The deadbeat controller, the reason why I chose it is because it's very intuitive and it doesn't include a PI controller or any other advanced control theory. So in order to understand the inverter, we first have to look at each component. So first we have the grid voltage, and it looks like this. So it's sinusoidal and each phase is 120 degrees phase shifted from each other. And then we have an inductor for each phase and then a half bridge for each phase. So if you look at one phase only, you can see that it looks like a boost converter. And then the three boost converters connect at the DC link voltage. However, it's not like a regular boost converter because all of the phases are connected somehow because the DC link voltage is floating. So the negative side of the DC link voltage looks like this. So you can see that it goes from minus 800 to 0 and is on average minus 400. And then if we look at the positive side of the DC link, we have kind of the opposite, so 0 to 800 and on average 400 volts. Now, in order to simplify this, I will not go through how to do the voltage control or the power control. I will just hand you a reference current, which looks like this. It has the same waveform as the voltage, but it's only scaled, so it has a lower amplitude. Now, we want to look at the voltage loop of the inverter. So we know that the grid voltage, VAC, which is the voltage here, reference to ground, must be equal to the voltage over the inductor, which is VL, plus the voltage at this point, which we can call Vm. So obviously, these are vectors, so they contain all phases. But in this equation, we assume that each phase is independent while they're not actually in reality. But this is a simplification we do. So we can control Vm. So we want to solve for Vm because we want to find the optimal Vm. So Vm equals VAC minus VL. So VAC is fixed, so we can't do anything about that. That is just measured. But we can calculate the desired VL. So VL must be equal to the inductance times the change of current over the change of time. So now it's maybe time to explain how a deadbeat controller works. So if we have the reference current, and then we have the actual current. So for example, let's say that we're at this point here. We want to find the optimal, or we want to find the change of current such that we get the reference current at the next period. So the change in current, in order to make this happen, so which is delta IL, this is equal to the reference current minus the actual current, which is just this point minus this point. And this needs to happen over a time period, over one switching period. And one switching period is 1 over F switching frequency, over the switching frequency. So that is how we find the desired, so if we insert for the change of current, the change of time and the change of current, we get the desired voltage over the inductor. And then we can insert this into the equation for Vm, and that results in this equation for Vm. And that is exactly what we're implementing into the Simulink model. So first we have the reference current and then minus the actual current, that is this part here. And then we multiply by the switching frequency and the inductance, that is this part here. And then we take the voltage of the grid minus VL, so this is VL. And then we get VM. Now I'm just going to wipe this out, because what we want to find out now is, so we have VM, and we want to find the duty cycle, which is here. So if you remember, the Simulink is floating. So we first have to get an idea of how does VM look like. So at the top here, we have 400 on average. And at the bottom here, we have minus 400 volts on average. And just to make a rough simplification, we say that they're always 400 and minus 400 in order to be able to operate each phase independent of each other. So now, for instance, if we look at one phase of the MOSFET in one phase, when the gate signal here is 0, then this MOSFET is open. And this means that this one is closed. So the voltage at this point needs to be equal to the voltage here. So VM becomes equal to minus 400 volts. Now, if the MOSFET is 1, or the gate signal is 1, then the opposite happens. Now this one is closed. So the voltage here becomes equal to the voltage here, which we've set to 400 volts. Now we can use this further, because we have another equation for VM, which is dependent on the duty cycle. So that is duty cycle times VDC. So remember that this is constant and 800 volts. Now, if we solve for the duty cycle, we get VM over VDC. So the reason why I do all of these calculations is because we want to find how we should set up the PVM, because it needs to be on the interval of the duty cycle. So the highest possible duty cycle is when the MOSFET or the gate signal is always 1. So in that case, we have that the duty cycle, we can calculate that if we just insert 400 here. We get 400 over 800, which is equal to 0.5. So that is the maximum duty cycle. And then the minimum duty cycle is just to insert minus 400 in for VM. So then we get minus 0.5. So that is the interval of the duty cycle. So we can insert that for the carrier. So I just delete that. So now you can see that the carrier is defined between minus 0.5 and 0.5. And this makes the converter work. So you can see that the duty cycle for one simulation result is between 0.5 and minus 0.5 as we predicted. So this is in steady state where there is no overmodulation. So if we look at the current, you can see that it is controlled. So the ripple here, the current with the ripple is the actual current, and the sinusoidal one is the reference. The reason why there's patterns in the ripple is because I have only 1 microsecond of step time. This was to decrease the simulation time. So that is basically how a 3-phase inverter works and how you can control it with a deadbeat controller.